Who's gonna win tonight, Professor?
Tonight.
Lakers, Denver.
Oh, it's opening night? I didn't realize that. I mean, Lakers, obviously.
No, it's hockey season.
Oh my God, I didn't realize it's starting today.
Yeah.
I've been so wrapped up in NFL that I didn't realize NBA was starting.
It's hockey season, so nothing else matters.
Okay, fair, fair.
Realistically, though, the Lakers are kind of that.
I heard the hockey season's over now.
No, it's getting started.
It's much better now.
Yeah.
I can go home and watch NBA.
So you're letting us out
Hockey
early?
game on right now.
So class is ending early?
No.
Yeah, I know. It's a 4:30 game, so we'll catch second half.
Stupid Denver.
Yeah.
Well, Ducks are.
Hey,
starting at 3:30.
Extra credit,
Right in
Lakers
the East Coast right
Huh?
now.
extra credit, Lakers one.
Yeah, actually could have been.
I've been thinking, the year they won the championship, I was thinking about it. No, I get trouble with that.
Hey, I want the department of just add like 2% to the touchscreen.
They find out of it. They look at all the great. It's 4 o'clock. Let's go ahead and get started. All right. Good afternoon, everyone. How's everyone doing today? Doing good. All right. So I brought the exams back today as well. So if you didn't get a chance to pick up the exams on last Thursday, pick it up today. Okay. And so I think the average last time was about 40 out of 50. So you guys are really good on the exams. Okay, so the plan for today, today is going to be a little bit of a transition day, and so we're going to talk about direct root methods, and so that's the last 1D method that we're going to go over today. So that'll be good. Okay, and then from there we'll move on to multi-dimensional nonlinear programming. Right? So the next set of lecture notes that we're going to go over, to me, I kind of consider that to be kind of the main part of the course. A lot of the algorithms that we're going to go over in the next section, in my opinion, are kind of some of the more important ones to know from this class. And in fact, you can use a lot of those algorithms in the final project, which I'm just about ready to kind of present to you guys. So I think the timing will work out just really well, because I think today we'll be able to get through Monte Carlo methods, and then I think that's kind of a good launching point from for the project. So Thursday we'll talk about the final project. You'll have about a month and a half to do the final project, and it'll be due the Monday after final. But we'll talk about it. Okay. Okay. And so another thing I want to do today, just because I know I haven't really had much of a chance to do it just yet, just because we've been talking so much about the algorithms, is that for everything that we're covering, ever since we started on linear programming, there's basically I've written an example code, and I posted it on Canvas. I think I might have shown one just very briefly, but I wanted to make sure that you guys are aware of it, and the fact that you guys can use it too. So homework 4 is I know due at the end of this week, and so I want you guys to be able to do I want you guys to be able to understand the algorithms too. So I do want you to do at least half of these by hand, but you can actually use the codes to run these problems as well. In fact, they're designed to kind of do that. And so, I think there's, kind of as traditional in my homework assignments, problem 1 is a kind of a short answer conceptual problem, so that one doesn't really count. But then problems 2, 3, and 4, each of them have 2 parts to them. And so for each of the problems 2, 3, and 4, for one of those parts, you can actually solve it via the code. And it's actually going to be a lot faster than solving it by hand. So for each part, you can choose either part A or part B of problems 2, 3, and 4. You have to do at least one of them by hand. but then the other one you can use the code for, and we'll talk a bit about how to do that today. Okay. Okay, actually, let me write that down just so it's clear. And so I'll let you choose either part A or part B of each problem. You can use the code to do that. Okay. All right. I think that's all my announcements. So are there any questions I can answer before we get started for today? Okay. All right. So let's go and get started. So actually, the first thing I want to do is I want to jump back to interpolation methods for just a second. So I know we kind of spent way too long on interpolation methods, but I did want to show you the code in terms of how that works. Okay. And in fact, I think this will be a good opportunity to kind of show you, where the code is on campus. So let me go ahead and switch to the computer screen here. Whoever was using this computer before me was a serious gamer because the sensitivity on this mouse is like a bazillion. I don't. I've never been too much into like FPS games and stuff, so I prefer my grandpa, slow mouse. Yeah, just me. Mandatory password change. Okay, and so if you go to the site here, I think what I'm going to try to do is I'm going to try to post the example codes for each week in the weekly pages. And so if you go to week 10 right here, you'll see. Oops, I can't post it for this week, but I will post it for this week. And so if you're looking for a specific code, though, I think the best way to find it is through the Files tab. Okay. And so in the Files tab, you'll see that there's a folder here for code examples, and so you're going to go ahead and click on that. And you can see here that I have a lot of example codes, and they're all labeled based on kind of what algorithm, what category of algorithms that they're solving. Okay. And so far, we've only gone over the 1D methods. So you'll see all the 1D code that I have here. So the first code that I have here is unrestricted search, and so this is kind of the first one that we looked at. Okay, so it's very short. This one is dichotomous search, and so I've gotten a couple questions about dichotomous search on the homework, and so the homework did mention that you can use dichotomous search. We're largely going to skip it, just kind of for time constraints, just to make sure we can get to all the other important stuff. But if you were interested in learning about dichotomous search, then I do have the example code here, and the details for the algorithm are in the lecture notes posted on. Okay, the one I did want to go over was this one, which is quadratic interpolation. So actually, let me download it, just so that you can see it. And then you'll see the remaining two codes here. One is for Newton-Raphson, and so we're going to go over that one later today. And then the last 1D code is for quasi-Newton-Raphson, which we'll cover previously as well. Okay. But all of these codes are available here online, and I've written these example codes in a way such that you can kind of easily kind of change them and apply them to different optimization problems, which I'll show you. Okay. So here's the example code here for the interpolation methods. So if you, I know some people have already attempted this one. So if you're struggling in particular with part B of the interpolation problem, this might be a good place to start. Okay. All right. Okay, so you can see here that, if you recall, the way our interpolation method works is that we're essentially trying to find out or trying to determine a surrogate function that will approximate our function as closely as possible within a certain domain. Okay, and so it starts by defining a certain step size. And then we're going to evaluate 3 x locations, so xa, xb, xc. Okay, and so xa always starts at 0, xb starts at t, and xc is 2 times t. Okay, and then we evaluate our objective function in our 3 locations. Okay, so this is fa, fb, fc. Okay, and so if you were going to apply this to our homework problem, this is where you would change it to. So, I think the homework problem, the objective function is different than the one we have here. And so you would change this so that, you would evaluate each objective function, or the objective function in each of our x values, x, b, x, and xc. Okay. Okay. And so from there, we launched into the first step of the algorithm, which is finding the appropriate step size. Okay. And so if you remember, the first thing we did for the interpolation method was we determined, whether we need to increase our step size or decrease it. Okay. And so this code right here is basically written so if we need to decrease our step size, then we go ahead and do just that. Okay. And so we need to decrease our step size if our FB is greater than our FA, right? So we want our FB to be kind of near the minimum of our function. And so we have a while loop here. So while FB is greater than FA, okay, then we are going to have our step size. So that's what this line of code does. But you can see which. Okay. So you can see here we're setting step size equal to 0.5 times step size. So it's half of what it was before. Okay. Then we're recomputing each of XA, XB, XC, and FA, FB, FC. Okay, and so once we recompute with the reduced step size, we're going to go back and check and see if FB is greater than FA. If it's not, then we're good. Then we can go ahead and move on to the next case. Okay. All right, and so that's the case if the step size is too small. If the step size were too big, this is the condition that we had to check. So we had to check to see if FB is less than FA and if FC is less than FB. Okay. And so if both of these are true, that means we need to double the step size or increase. Okay. So that's essentially what we're doing in this line of code right here. Okay. And then just like before, we're gonna reset or recompute XA, XB, XC with a new step size and evaluate our objective function 3 more times. Okay. And so ideally, once you kind of reach the end of these 2 while loops here, then our step size is perfect, right? So we're kind of in that kind of perfect case. And then from there, we kind of iterate on step size, okay? And so from there, we're going to compute the location of the minimum. We're going to compute the objective function value at the minimum, okay? And then from there, we're going to check and see, if we're converged, okay? Okay. And so if we're not converged, and so remember the way that we check convergence is to check and see if our surrogate function and our original objective function had the same, basically the same value at the minimum. Okay? And if it's not, then we're going to go in and kind of change the values. And so if you kind of recognize here, this is kind of our 4 different cases. And so this is kind of the second part of the algorithm where we're defining our surrogate. So depending on the relative values of x min and the step size, and the value for the original objective function at the minimum relative to FB, we're gonna make adjustments to XA, XB, and FA and FB, according to these formulas. Okay. All right. So from there we recompute. The values for A, B, and C. We compute the minimum again, and then we exit there, and then we check and see for convergence again. Right? And so the main part of the interpolation algorithm is in this loop here, starting with line 68, right? Okay. And then from there, once we have it, then we can plot it, okay? And we can plot the surrogate, and then that's the end of that. Okay.
Pretty much the only thing that we're changing is at the top, just our equation.
Exactly. Yeah. Basically, whenever you see the objective function. So actually, we evaluate the objective function several times here. Basically, anytime you see this function right here, you're going to change the objective. You're going to change that to whatever your current So this was maybe not the best example because the interpolation algorithm actually does have quite a few steps. But I think, this will be useful to go through as well, because we did go through the interpolation algorithm in kind of excruciating detail with the example. Okay, and so kind of lining up what you're doing with the nodes and kind of seeing what's being done in the code, I think is a good exercise, because that's kind of something that's kind of an important skill that we're going to need going forward, is kind of taking what we're doing in the lectures, taking kind of what we're talking about in terms of the algorithms, and then translating that into code is a useful skill. Okay. And I wrote these codes so that they can be a companion together with the in-class examples. Okay. And so if you kind of follow your in-class examples exactly, this code here is going to do the exact same thing. Okay. And so I always recommend people to look through the code, look at it together with the in-class notes, so you can kind of understand what every single line of code is doing.
Yeah. So when we choose the step size, and the step size is what we choose it to be, and then later down you have the code that kind of this code, so it makes adjustments, and then it spits out a new step size.
Yeah.
Does that get put into our workspace? And
it does.
Okay,
it does.
that will tell us the new step size, or we can just kind of see the step size that we put and see the one in our workspace and see it.
Exactly, right. So the one that we define up here is just the starting point. And so from there, the code is going to adjust it. So after you run the code, then the actual step size, the one that you need for the algorithm, is going to be put in workspace. In fact, let me run this code just so you can see. Because I think for this example, we ended up not using, I think we started with 0.5, but I think the step size we ended up with is 2. And so let me go ahead and run this code just so you can see. Okay. So the plot here is actually quite nice. And so in blue right here, what we're seeing here is our surrogate function. So that's our quadratic function that we're using as a surrogate. And then in red here, that is our original objective function. Okay. Okay. And so for the step size, let's see. Yeah. And so you can see here that the step size has been updated to 2. So even though we started with 0.5, the code adjusted it automatically to 2. Okay. Yeah. And you can see we reached convergence after 7 iterations. Another question I got last week from a few people, actually, a lot of emails, is that for these examples that we're doing, these are not the kind of the best examples for nonlinear programming, because these objective functions, the ones that we're evaluating here, we actually do have an explicit form for this objective function. So in reality, we technically don't need interpolation methods for this. So we can just we can either plot this function, we can either take derivatives, we can find the minimum here in a lot of different ways. But the reason I'm giving you this kind of problem is first of all, I know for a fact that there's an answer that exists. And I think working with a function like this, which is easy to evaluate, I think kind of cuts down a little bit of the mental process, because there's a lot of other things going on in the algorithm. So kind of having a more complicated objective function, or maybe one where you can't really see kind of its mathematical form, I think will be a little bit different. So, but technically speaking, yes, if you have an objective function that looks like this, it's just a bit or a polynomial. You can take derivatives and you can set it equal to 0 and find the minimums exactly the same way. I just chose it for this example just because it makes the algorithm, I think, a little bit easier to do. Okay. Okay, and so if you wanted to use this code for your homework, so this would be problem 3 on the homework, either part A or part B. You're certainly welcome to do so. You just have to make the adjustments to the code as necessary for the objective. Okay. All right. Question. So in the homework, it asks us to use a surrogate accuracy threshold 0.1. Should we edit the code to stick to that value? Should we keep the conversion? Oh, that's a great question. Yeah. So in the code here, okay. Yeah, so what Christine was asking about was that in the homework, this value right here is basically your epsilon value. Right? And so this is the threshold that basically tells us to stop refining our surrogate. And so in this code here, I'm using a pretty tight threshold. And so what this is basically saying is that the difference between the surrogate and our original function should have an error of less than, in this case, it's 0.01%. But in the homework, what I tell you to do instead is to change it to 0.1. Yeah. And so the reason I did that for the homework is that if you were doing it by hand, you know, if you try to use a tolerance of 1 e-4, you know, you're going to be iterating, you know, dozens of times. So the problem is almost never going to end. But for the code, you know, you know, iterating a dozen times is no problem. So, and so if you're going to use the code, you know, I would say, you know, let's go ahead and use a tighter tolerance. But if you're going to use hand calculations, then you can use a threshold of 0.2. But you know, if you're not sure, then you can just use 0.1 for both the code and the hand calculations. But you know, if you're going to use the code anyway, and MATLAB's going to do most of the calculations for you, you know, you might as well try a tighter tolerance. In fact, you could try an even tighter tolerance. So you can do 1 e-5. You can see how that works out. Good question. All right. Any other questions on this code here? Okay. All right. So let's get back to talking about direct root methods. Okay. Okay, so direct root methods is kind of the last one-dimensional method that we'll kind of mention in this part of the class. Okay, I think I mentioned last time that direct root method kind of has applications that kind of go far beyond optimization. You know, so I think it's, you know, we're here anyway. We might as well talk about it, just because it's very important. It's a great method. Okay. And so the method that we're going to be focusing on is one that's attributed to Isaac Newton. Actually, it's more attributed to one of his students, but Newton gets his name on it because Newton is the most famous. Okay, and so this method is called the Newton-Raphson. Okay. So Raphson was the student of Isaac Newton. You know, fortunately, he gets his name gets to go second. Okay, and so the idea behind this method is to iteratively find the locations for a given function where its first derivative is 0. In other words, we're going to look for the location where df dx, where f here is our objective function, as it usually is. We're going to look for the locations where df dx is equal to 0. Okay. Okay, and so this sounds like our classical methods, right? And so this doesn't seem like it's anything new. And so in essence, you know, the idea is the same as our classical method. So we're still going to find the location where our derivative is equal to 0. It's just the way that we're going to do it is going to be different. Okay. And so the key word here is actually the very first word in this definition, which is iterative. Okay. So technically, you know, all the algorithms that we're covering from this point on in the class are iterative methods. And so what an iterative method basically means is that it's something that has to be repeated over and over and over again. You know, sometimes it only has to be repeated 5 or 6 times, but you know, many times you have to iterate, you know, maybe hundreds or thousands or sometimes even millions of times. Okay? Because the way that we found the locations where the derivative was 0 before was basically algebraic. So we algebraically took the derivative of the function and we algebraically solved for where it is 0. Okay. All right. And so the idea is this. So instead of solving for this algebraically, what we're going to have instead is kind of almost like we call it a recurrence relation. So we're going to have basically a way to improve our guess. Okay. And so the way Newton-Raphson works is that we're going to start with the guess. Okay, so we're going to start with a guess for where df dx is equal to 0. So let's call this X naught because it's the first one. So your initial guess does matter, and so you can't just guess, 11 billion, right? And so it ideally should be somewhat close. Sorry, are you guys listening? You guys put on headphones? Okay. So we'll call it our initial guess X naught. And then what we're going to do is we're going to improve our guess using this relationship. And so what we're going to say is we're going to say X at I plus 1. Okay. So I plus 1 represents kind of you can almost think of it as like our next guess for the root. Okay. This is going to be equal to Xi, which was the previous guess, minus F prime at Xi divided by F double prime X. So this Xi plus 1, this is our next guess. Okay. This Xi is our previous guess. And on the right, that last term there is a ratio of the first and second derivatives of the function evaluated at our previous guess. All right, and so what the Newton-Raphson method says is that if we use this relationship here and we basically just repeat this over and over and over again, then eventually we're going to converge to the location of the root. Okay. In fact, it has some superconvergence properties where if your original objective function was quadratic or close to quadratic in nature, I think the Newton-Raphson method will actually converge in just one step. Okay. So before we do an example for this, there is one very important caveat here. Some of you may have picked up on it already. Okay. And so the one important caveat for this function is that we do have to have explicit expressions for the first and second derivatives, which kind of seems to break the whole rule of nonlinear programming. So we're actually not supposed to use derivatives. Because the whole point of nonlinear programming is to have optimization algorithms that don't rely on the derivatives, okay? And so don't worry about it, there is a way to get this method to work without the derivatives, and that's called quasi-Newton Raphson, which is, for our cases, is gonna be the more common, the more common algorithm to use, okay? But before we get to quasi-Newton Raphson, we should at least kind of see how regular Newton Raphson works, just so it's a little bit easier to use. Okay, and so with that, I'm about to do an example, but are there any questions on this before we get there? Okay, all right, so let's do an example. In fact, this is a, it's a objective function from the homework, but it's, but I don't have you solve it using Newton Raphson. So, this function should look familiar, but it's not part of the problem. Okay. All right, so what we're going to do is we want to find the minimum of the following function. Okay. So we have f of x is equal to 0.65 minus 0.75 by 1 plus x squared minus 0.65x and inverse 1 over x. Okay. All right, so this function is a mess, and so there's a lot going on with this function. So taking the derivative of this function actually is not going to be fun. So this is actually kind of a good example of when to use nonlinear. Okay. All right, and so what we're going to use is we're going to use Newton Raphson. With an initial guess of 0.1. So I'm going to say x naught is equal to 0.1. Okay. And let's iterate. So anytime you have an iterative algorithm, you have to have some kind of way to stop it. And so usually that takes the form of some kind of error threshold or convergence criteria. Okay. And so if you remember from the interpolation methods, we had our convergence threshold that we defined. And so for Newton Raphson, that's going to take the form of whatever the derivative is. Okay. And so let's iterate until our value for f prime of x min is less than or equal to 0.01. Okay. Okay. All right, so that is our problem here. Okay, so ultimately we're going to use our Newton Raphson. So our Newton Raphson basically saying that our next guess, we'll call it x1, okay, is equal to our original guess, x naught, minus f prime of x naught divided by f double prime of x naught. So x naught we know already. We know we're given that in the problem. So x naught we know is 0.1. Okay. So we're off to a good start. So 1 out of 3 terms is determined. Okay. But in order to use this, we actually have to take not only the first derivative, but the second derivative as well. Okay. And if you're going to use regular Newton Raphson, there's kind of no way around it. You just have to compute the derivatives by okay. Okay. So I'm going to skip you that pain. So I'm not going to, we're not going to go through all the chain rule and product rule stuff. Although certainly if you like doing that, then the details for that are in the notes. But I'm just going to go ahead and skip straight to it. And so if you take the derivative of this kind of monstrosity of a function, you get the following. So we get 1.5x divided by 1 plus x squared, quantity squared, okay, minus 0.65 and inverse of 1 over x, okay, plus 0.65 x times or divided by 1 plus x. Okay. So this is something that you can obtain after a lot of angle and product. It's not that much actually. It's only 3 lines of work in the. All right. But hopefully, you can see from this functional form why Newton-Raphson is actually really useful in this case. So even though technically we do have an explicit form for the derivative, if we were to set this equal to 0, and I were to tell you to solve for x in this situation, you probably leave me a lot of negative comments on the YouTube. So we're not going to do it. Okay? We're going to use Newton-Raphson instead. But to use Newton-Raphson, we have to take one more derivative. So let me give you the final form for that. And so if you take one more derivative, we end up with 1.3 divided by 1 plus x squared plus 1.5 minus 1.3 x squared, all divided by quantity 1 plus x squared, quantity squared, minus 6x squared, divided by 1 plus x squared, quantity. Okay. So lots of chain rule and lots of product rule, and within that, we have a derivative of tan inverse x as well, which is 1 over x squared. So that's kind of why the tan inverse kind of disappears from the. Okay. All right, so now that we have the functional forms for for the derivatives, let's evaluate these at x naught. So setting these equal to 0 and solving for x that way, that's a little bit too difficult. But what we can do is we can evaluate these, and because that just involves plugging in. Okay. Okay, so this will be iteration. We'll call this iteration 1. Okay, so for iteration 1, we have x naught is equal to 0.1. Okay, that's our initial guess. Let's go ahead and evaluate f prime of x naught and f double prime of x naught. Okay. And so to get those, all we have to do is we just have to plug in x naught into our 2 functions above. Okay. And so we plug in x is equal to 0.1 into the first derivative. So you do that, we get minus 0.745. Okay. And then we plug in for the second derivative, we plug in x is equal to 0.1. What we get is 2.687. All right. And so if we take this information, we're going to go ahead and compute x1. So we know that x1 is equal to x naught, which is 0.1, minus f prime of x naught, which is a minus 0.745, divided by f double prime of x naught, which is 2.687.
Isn't the iteration 0.0
so that's the convergence threshold. So that's the so our initial guess was 0.1, and then our convergence threshold was 0.0. Okay, and so we punch this into a calculator, and what we get is 0.377. Okay, so this right here is our new guess. Or where the f dx is. Okay. It may not be exact yet, but it at least we're going in the right direction. At least the hope is that we're going in the right direction. Okay. Okay. So let's check convergence. And so for convergence, what we're basically are requiring is that when we plug in our guess for f for x here, x min, then we should get f prime of 0. Okay? So check, we're going to see if f prime of x1 is equal to 0. Okay, question mark. So we plug in x1 into our equation up here. And so we plug in x1, we get f prime of x1 is equal to minus 0.13. And so we can see from this that we are not converged. And so we're going to have to do another iteration. Okay. So let's go ahead and go on to iteration 2. All right, so for iteration 2, we're going to start with a value of x1 is equal to 0.377. Okay. From here, we're going to evaluate f prime of x1 equal to f double prime of x1 equal to. Okay, so this is just plugging in our x value here, and so we've already computed x prime, so this is minus 0.138. And then f double prime of x1, we plug in x1 for that, we get 1.57. All right, so we can now take this information and solve for x2. So x2 is going to be x1, which is 0.377 minus f prime of x1, which is a minus 0.138 divided by f double prime of x1, which is 1.573. Okay. And so our next guess for x min is going to be 0.465. Okay, so let's go ahead and check convergence for this, and so we're going to do the same thing. Okay, we're going to check if f prime of x2 is equal to 0. Okay. And so we plug in x2 into our f prime equation. What we get is minus 0.0179. And so you can see from this, we're not quite there yet, although we are very, very close. Okay. So let's go ahead and iterate one more time. I go pretty fast on this one. And so we have iteration 3. So we're going to start with the value of x2 equal to 0.465. Okay. And just like before, we're going to evaluate f prime of x2, f double prime of x2. Okay. And so we're going to plug into our expressions here, and then f prime of x2 is minus 0.0179, and then f double prime is 1.171. Okay. Okay. And so from that we compute x3, and so this will be 0.465 minus 0.0179 divided by 1.171. Okay. We punch that into a calculator, we get x3 is equal to 0.4805. Okay. And so let's check convergence one last time. Well, I kind of spoiled it. So this is going to be the last. This is going to be the last iteration. Okay. Okay. so checking convergence, what we have is f prime of x3, okay? So now that we've updated our guess, we're gonna compute the derivative at that point, and what we get is minus 0.0000. And since our derivative here is almost zero, it's basically zero, or more importantly, it's less than our threshold, then we've reached convergence for our order product. Okay, and so based on this, what we can say is that the minimum of f of x occurs at x is equal to 0.480. All right. So that's Newton-Raphson in a nutshell. So once you have the derivatives, then it's kind of just a kind of a plug and chug, and you just kind of repeat it until you reach convergence. Okay. And Newton-Raphson is so good, it's almost guaranteed that if a minimum does exist, you will find it eventually using it. All right, any questions on this example here? Okay. All right. And so last thing I want to cover, in the 1D methods is quasi-Newton-Raphson. Okay. So quasi is not a person's name. So quasi was not another student of Newton. It was just it's just kind of a buzzword that's used in mathematics to say this is kind of like this method, although it's not quite. And so we call it quasi Newton-Raphson. It's Newton-Raphson in spirit, but it's not exactly. But it's in this case, it's actually pretty close. Okay. And so the main I would say the main criticism that we have for Newton-Raphson is that in order to actually use it, we need to compute the function derivative and its second derivative. It's a little bit better than our classical methods because we don't actually have to find the roots of this of these functions. But sometimes computing these derivatives can either be one, extremely cumbersome, and so they're just not practical to do, or it's literally impossible. So you have an objective function where you can't take the derivatives. Okay. But in these cases, we still want to use Newton-Raphson because it has a lot of nice properties. But if we can't take the derivatives, then we have to kind of accomplish this a second way. Okay. All right. And so another way to do Newton-Raphson is to not explicitly compute the derivatives, but instead to approximate them using something called finite differences. And so if you're unfamiliar with finite differences are a way to approximate derivatives of a function using only its function evaluations. Okay. And so for instance, if we want to approximate f prime of x1 or xi, okay, the way we would do this is we basically take two function evaluations. So we take f of xi plus delta x, okay, where delta x is kind of some small step size. Then from that, we subtract f of xi minus delta x, okay? And then we divide the whole quantity by 2 times delta x, okay? And so this formula here, instead of actually computing the derivative, we can approximate it using these, using these finite differences, okay? And those finite differences only rely on function evaluation. So this is kind of more true in spirit, kind of all the other algorithms that we covered, which again, also only depend on function evaluations, okay? All right, but of course, the caveat here is, we have to choose delta x. So delta x is, some small step size. For this case, for doing quasi-Newton-Raphson, it doesn't matter too much what delta x is. You just want to choose one that's kind of sufficiently small. Okay. And we'll talk about that in a second. Okay, so that's the approximation for the first derivative. We also have a finite difference approximation for the second derivative. And so for the second derivative, we have the following: x f double prime of xi is equal to f of xi plus delta x, okay, minus 2 times f of xi plus f of xi minus delta x, and this whole quantity is divided by delta x. So this function here requires one more function evaluation relative to the first derivative. But again, this kind of avoids us taking any derivatives, or at least any explicit derivatives, which is really okay. So we can take these two expressions and we can plug them into our Newton-Raphson iteration, and then we can update it to only require function evaluations. Okay. And so, let's have our updated equation here. So x of I plus 1 is equal to xi minus, okay. And so there's some algebra here, and so I'm just going to go ahead and simplify that algebra for you. I'm just going to give you the final expression. So it's going to be delta x divided by 2 multiplied by f of xi plus delta x minus f of xi minus delta x, all divided by f of xi plus delta x minus 2 f of xi plus f of xi minus delta x. So this is really nice right here. And so it looks longer and it looks more cumbersome than our original Newton-Raphson. But instead of actually having to compute the derivatives, we're only computing function evaluations here. So this is kind of more in spirit with the rest of our algorithms. So this right here is our Newton-Raphson. Updated. All right, so for this one, let's look at the code. So I have a code for regular Newton-Raphson as well, but I think the one that's going to be more useful to you overall is going to be quasi. Because I can see you guys using this one on the project more so than the. Okay, so let's go ahead and see example code. I believe the name of the file is 1D NLP example 5. Quasi Newton. All right, we're going to look at that in a second, just so you can see how that's. Okay. All right. Before we do that, any questions on this? Okay. All right. So let's take a look at that code. Just because. Should be this. Yeah. 1D NLP example 5 quasi. This. Okay. All right, so this is the quasi Newton-Raphson. So you can see that the code here is actually a lot shorter, which is actually quite nice. Okay. And I've done something here to kind of simplify things as well. And so if you remember from the interpolation code, I kind of almost hard coded the objective function into the code. And so if you were to make a change to the objective function, you have to change it in several different places. But I made kind of a clever use of functions here in this program, so that if you were to change the objective function, you would only have to do it in one place, which is down. I'll explain that in a second. Okay, that's the other reason why I wanted to do this this example. Okay, and so just like our interpolation algorithm, or just like a normal Newton-Raphson, we have to start with an initial guess. Okay, and so in this case, our initial guess we're going to start with is 0.1. Okay. The other thing that we have to do for Newton-Raphson is we have to define our step size. Okay, and so this dx here is our step size for computing finite difference approximations. Okay. So that's the delta x term that we had in the expressions above. Okay. And then just like any iterative algorithm, we need some kind of convergence tolerance, and so some way to kind of tell us to stop. And so in this case, it's going to be 0.08. Okay. Okay. All right, and so here we see kind of where the function takes place. Okay, and so at this point here, you can see from the comment that we are evaluating our objective function and derivatives at the initial point. Okay, and so just like normal Newton-Raphson, we start from our initial point, and then we have to compute our objective function and our derivatives at that. Okay, and so normally right here we can see that we would normally compute our objective function here, but you can see instead I'm using this function called f-eval. And so this is kind of a nice trick that you can use within MATLAB. So and actually it'll be very, very useful for you doing optimization in general. Okay, and so generally what I recommend is if you're going to use a code like this and you know what your objective function looks like, you can actually define a function here in MATLAB to compute it for you. Okay, and so if you've never used functions in MATLAB before, the way they work is that you have to put them at the end of the code, so they have to be kind of the last thing, and you use a keyword function. Okay, and so the way this works is that basically you have to give a name for your function. So in this case, I'm calling it f-eval, and then the function takes in some argument. So the arguments in our case are usually going to be the design variables, or whatever our x variables will be. Okay, and so since we're doing a 1D optimization, I'm going to put in one value for x. Okay, And then the return value is going to be eval, okay, whatever we define that to be. And so inside the function here, you can see that I've written out the objective function here, right? And so what I'm saying is that eval is equal to 0.65 minus 0.75 divided by 1 plus x squared minus 0.65 times x times arctangent of 1 over x. Okay, so this is the objective function that we're working with in this problem. Okay. And so I've implemented that in just one location in the code. And so from now on, whenever I need to call this function and evaluate it at a certain value of x, I'm only going to call this function f eval. Okay. And so if I scroll back up in the code here, so if we look at line 15, okay, line 13, you can see here that we're evaluating our objective function at our initial function. And so instead of typing out kind of the full objective function, the only thing I'm going to do instead is just call f eval here, and I'm going to evaluate it at x. Okay. Okay, so any questions on how to make use of the functions in MATLAB? Because it is something that's going to be really useful. And in fact, if you're going to use this for the homework, the only thing that you have to change is you have to come down here and change this, change what's in this function there. And so we'll kind of see this a lot more often as we get to the other parts of the other algorithms. Okay, yeah.
Are we always given the initial guess, or are we going to learn to get that too?
So for this class, yes. For this class, you're always going to be given an initial guess. And when you're using optimization in real life, you're not going to be given an initial guess. Usually you have some kind of idea in terms of where your optimal design is going to be. And so let's say, for instance, you're optimizing the design of a cylinder, right? And so you're deciding the values for the radius and the length. And so, usually before you start, you have some kind of idea where, like, you're not designing like a missile, you're designing like a water can. So you have like an approximate dimensions of what a water can looks like. And so that's usually where you get your initial guess. And so it's usually not a complete shot in the dark. You usually know kind of the ballpark or the neighborhood.
Code break, like a large number.
So for this one, I think you actually can use a hard number for this one and actually convert to the right one. But in reality, the algorithm is a little bit sensitive to that initial guess. So if you guess a little bit too far, like if you put 1 billion, I think eventually you might get to the minimum if it's a monotonic function, but it's just going to take you a lot of iterations too. Okay. And so from there, we have to compute the first derivative. So you can see here the way we're computing the first derivative is we're using finite differences. Okay. That comment ended up being a little bit too long, but you can see here that this is our finite difference formula. So we're evaluating our objective function at the initial guess plus dx, and then the initial guess minus dx. Okay. And then we're dividing the whole thing by 2 times dx. And then for the second derivative, you can see we're plugging into our finite difference function for that. So we have f eval at x guess plus dx minus 2 times f eval at x guess plus f eval at x guess minus dx, all divided by dx squared. Okay, so these two lines of code, lines 14 and 15, are the finite difference approximations for the first and second derivative. Okay. And so from there, we enter our iterations, which is actually quite short. So, the way the iterations work is that, remember, the way we're checking for convergence is we're checking to see if the derivative is equal to 0 or if it's less than the convergence tolerance. And so while this derivative here is greater than the convergence tolerance, then we're going to continue to iterate. Okay. And so a while loop is sometimes you'll see for loops in my code, sometimes you'll see while loops. While loops are a little bit more common just because of the way optimization algorithms are designed. And so you'll see those kind of a bit more often. Okay. Okay. And so inside the iteration, you can see here that we're updating our guess. And so we're updating our guess based on the previous guess. And then we're based on the first and second derivatives that we just computed. So that's df divided by d2f. Okay. You can see here that I'm using update notation. So I'm basically just overwriting whatever we had before. But this on the right side of the equation, this one here is basically xi plus one. And this is xi, so the previous guess. And so, what I'm doing is I'm computing what the new guess should be and just saving it into the same variable. So I'm just updating it from what it should be. Okay. And then based on this new guess right here, I'm reevaluating all of the function, objective function and its derivatives. Okay. And then I'm increasing the iteration count. This is just for my own records to see how many times we iterated. Okay. And then we check again. Okay. And so this part here will keep repeating until until our derivative is equal to 0. Okay. And so we're going to compute. We're going to check, see if we are converged. If not, then we update our guess. After we update our guess, then we update our objective function and derivatives, and then we check again. And if not, then we keep iterating over and over and over. And then the rest of this code here is just kind of printing the optimum to the screen. Okay, and so the way I've written this code here, it actually tells you the number of iterations. So let's go ahead and run this code. Okay, and so you can see here that running the quasi-Newton-Raphson gives us a converged value of 0.48. So that's pretty much exactly what we got from the regular Newton-Raphson when we did by hand. And we achieved this in 4 iterations. Okay. So a little bit slower. And so what you notice is it's a little bit slower than the original Newton-Raphson, just because we're using finite differences instead of the explicit derivatives. But we end up in the same. Okay, any questions on quasi-Newton-Raphson? Yeah. Yeah, that's a good question. So we can see. And so the step size here, in this case, the step size only is only for computing the derivatives. So we can change it. So we can make the step size bigger. Let's not make it 0.1. Let's make it 0.3. So let's see what effect that has. Okay, so changing the step size to 0.3, it still gets us in 4 iterations. And we get almost the same answers, just off. And so in this case, I guess step size in this case is a little bit of a misnomer. We're not actually taking steps in that much in each direction. It's only for computing the derivatives. And so in this case, the amount that we step in each iteration is actually determined by the update formula. And so the step size is kind of computed dynamically. And so I guess the better name for this step size is that instead of calling this a step size, maybe this is better called the finite difference. Yeah, good question. Because normally, for one of our other methods, changing that step size will either accelerate us to get to convergence faster, or it will slow us down. But the step size takes a little bit of a different definition. All right, any other questions on this code here? Okay, all right, and so that's it for one-dimensional methods, and so you should have everything that you need to finish homework 4 now. Okay, so we do have about 8 minutes left in class, and so let me introduce the idea of a multi-dimensional method, and then we'll kind of get more into it on first. Okay, question. So would decreasing the finite difference length make it more or less accurate? Technically, yes. And so when you're computing finite difference approximations, the lower or the smaller your finite difference length, the more accurate your derivatives are going to be. So actually, we can try and make it even smaller. So we try 0.001. And so in this case, it doesn't make too much of a difference because the function is fairly simple. But technically, yes, if you make that finite difference length smaller in this case, it'll compute the derivatives a little bit more accurately. And so your update formula will also be a little bit more accurate. So it'll kind of approach kind of regular Newton-Raphson. But for most cases, it doesn't matter too much what you pick for the finite difference length, as long as it's small enough. So usually what I like to do is I like to take my initial guess, and then I just multiply that either by or divide it by 10 or divide it by 100. And so as long as it's sufficiently smaller than your initial guess, then you should be in pretty good shape. Okay. Let's kind of come back here. the last 2 minutes here. Let's talk about unconstrained. And so, so the next topic here is, we're going to look at more nonlinear programming algorithms, but we're going to look at algorithms that work for multi-dimensional problems, which is, honestly, is kind of the vast majority of optimization problems. Okay. All right. So far, we've done one-dimensional problems. So the 1D algorithms are kind of, you can almost think of them as kind of like a warm-up. Okay. And so now we're going to look at, problems that involve multiple design variables. Right. So the reason I kind of start with the 1D problems is it's a good warm up. It kind of introduces you to the idea of what nonlinear programming is. Okay, and so the same ideas are going to apply. So all the algorithms that we're going to discuss. They are designed in a way to only rely on the function evaluation or objective function evaluations. So we're not going to do any derivative methods in this case. Okay. And so the general approach is the following, with one exception. So the only exception to this is kind of the Monte Carlo method, but Monte Carlo is kind of in its own category. But most of the methods kind of work in the following. And so it's actually quite similar to the Newton-Raphson method. So, at any given iteration or at any given point within the algorithm, we're going to have our current guess. For the optimal point. Except now that we're using and now that we're in multiple dimensions, this current guess is going to be a vector instead of just a point. Okay. And then what we want to do is we want to update this or improve this guess to get it closer to the true optimal point. All right, and so the way we're going to do that, in general, is going to look like the following. So we're going to have xi plus 1 vector. Okay. So this right here will be our improved guess. This is going to be equal to our current guess plus a parameter called lambda I, which I will describe in a second, multiplied by si, which is another vector. This xi here is our current guess. This lambda here is called the step point. And this SI here is the search direction. All right. And so the way to kind of interpret this, and you know, relative to a lot of, I think, mathematical algorithms and formulas, I think this has kind of a very intuitive kind of feel to it. Okay? And so the idea behind this is that, you know, think about our analogy of treasure hunting that we talked about before. Okay? And so think about the optimal point or the optimal design point to be where the treasure is located on some kind of sandy beach in n-dimensional math space. Kind of a weird image. And so, you know, we have our current location and we want to get closer to where the treasure is. Okay. And so the way we're going to get closer is we're going to take a step of a certain length, okay, in a specified direction. So that's all this formula is saying, is that, you know, we're going to take successive steps, and it's going to take us a lot of steps sometimes. So we're not going to be able to solve this in one step. But as long as we keep taking steps in the right direction, eventually we're going to converge, or eventually we're going to find where that optimal point is, where that treasure is. Okay. All right, and then, you know, we're going to be able to do this using only function evaluation, so no derivatives. Okay. All right, and so what you're going to see over the next few classes, and so, you know, we'll start looking at this more carefully on Thursday, is, you know, how can we use these, you know, in essence, it kind of seems very limiting to only look at just the function evaluations. But you'd be surprised that, you know, we can actually use the function evaluations kind of a very clever way in order to get us closer to the optimal case. And in most cases, you know, we're going to converge pretty reliably. It may not be the fastest thing in the world, but, you know, we are going to get there eventually. All right, any questions on this before we wrap it up for today? Okay, all right, and so if you haven't had a chance to pick up your exam, you can come to the front and pick that up. Thank you guys for coming today. Hope you guys enjoy the rest of your afternoon. I will see you on Thursday. Yep.
Forward iteration.
Oh, it should be absolute value. Yeah, because the basically, so this is basically iterating until we find a location where the derivative is equal to. So yeah, it should be absolute value.
Is this one of your? Oh, yes.